Record on this here computer for 250. Real ear. Last semester you had 240. Compressione, compression. This year it's more like fitting methods, real ear, but mostly real ear. But we want to touch on a couple of things to make sure that you got it. Okay? So one of these guys, if I share screen here and opt for this, and if you look at, where are we here? Okay. Can you guys see this right in the middle of my screen here? You can see the units laid out for you. Okay? You got a PowerPoint and a Microsoft Word document on non-electronic acoustic modifications, just to make sure we've got our acts together regarding venting, mostly vents. The other one, next week, we'll do a quick review of your ANSI knowledge. OSPL 90, reference test gain, harmonic distortion, equivalent input noise, all of that jazz. Okay? Then the week after, in week 3, we'll look at hearing aid fitting methods. And you've had that in 150. But I really want to emphasize that hearing aid fitting methods and real ear evolved together. They're like when you pull out of the garden and you pull out a couple of carrots and they're completely wrapped around each other. It doesn't mean that they're necessarily in love. It just means that they've totally evolved around each other. Fitting methods affected real ear, and real ear affected fitting methods. So when you took fitting methods in 150 and now you're taking real ear here in 250, it's important to make sure we review fitting methods as they evolved along with real ear. And that's kind of the vantage point at which I'll be describing it. So we'll look at early fitting methods, then we'll look at, of course, today's new fitting methods, NAL 2, NAL 1, DSL 5, all of that stuff. And then we'll get into old real ear as it evolved with fitting methods, how we used to do real ear, and somehow some people still do real ear, which they shouldn't. And then we'll look at today's real ear, which is mostly called speech mapping, as you'd see on the Metarex system, as you'd see on the Audio Scan system, the OtoSuite Oracle system. Any of these real ear systems use today's real ear, and it's often called speech mapping. And then we'll finish with Unit 7, where we'll really be looking at software talks and real ear measurement walks. And really, to be perfectly honest with you, that is the case. I mean, software predicts where you're going to be. Real ear proves it. And that's why they call real ear verification. If I stop sharing here, verily, verily, he said unto thee. Okay, truthfully, truthfully. In vino veritas, in wine there is truth. Real ear verifies. Questionnaires like the COSI. Have you guys ever taken anything called the COSI yet? Client-Oriented Scale of Improvement? Or Abbreviated Profile of Hearing Aid Benefit? Or Hearing Handicapped Inventory for Adults? Any of those are called satisfaction questionnaires. And satisfaction questionnaires aren't looking at the objective. Is the hearing aid doing what you said it was doing? It's how happy do you feel about the hearing aids? How do you like them? How do you find them at church? How do you find them at the supper table? Where do you have your most problems with the? It's more like a subjective questionnaire about client satisfaction about the performance of a hearing aid. And that's called validation. So when you see the word validation, think satisfaction questionnaires. And there's about 3 or 4 of them that are used in this field. Very commonly, one common one you'll see is the COSI, Client-Oriented Scale of Improvement, okay? And that's a real popular one. It's invented in the land down under by the people who started NAL, National Acoustics Labs Fitting Methods. Harvey Dillon, he's the one that came up with the COSI, okay? So that, but real ear is verification. So real ear is brain, objective, head. Validation is questionnaires, how do you feel? So I'm kind of surprised you haven't taken that. Maybe I'll throw that in there as a unit. What the heck? You know, the nice thing about OTC is your semesters are 15 weeks long. I mean, this is great. At Douglas College, where I teach here in Canada, 13 weeks max. You miss a week, you're screwed. OTC is just kind of like, hey, man, so you missed a week? We'll make it up the next one. Take a chill pill. I like that. I like teaching an OTC for that. So anyway, so that essentially gives you the breakdown of the field, because when you're looking at verification, fitting method software talks. Software, you'll pick a Phonak or an Oticon, and you bink in the hearing loss into NOAA, and you choose a fitting method, NAL 1 or NAL 2, and you do the quick fit, and it's going to show like it fits perfectly. It's going to show you really good results. You do real ear, enter the same audiogram into the real ear equipment, choose the same fitting method in the real ear equipment, put the same hearing aids on and measure with real ear. You'll find different, not the same, and it's almost always not as good. In other words, the software looks at things through rose-colored glasses. Just like, oh yeah. And the real ear usually shows a more bitter truth. And it isn't always like that, but that's why fitting methods, I should say fitting software, it's not their fault. I mean, they get you in the ballpark. They get you to pretty close to where you want to be, but it's our job as hearing instrument specialists to finish it. And that's why a lot of HISs out there who aren't doing real ear, because they've never had the training you're getting, and so they just let the fitting software do the talking and the walking. They do the fitting and then save it and healed, Jesus, go on ahead. You know, meanwhile, the guy's getting 4 dB of gain or something, you know, it's like, ah. So, and it's not the manufacturer's fault. They're not out there to mess anybody up, but it's our job to do the fitting, not theirs. Their job is to get us part way, because their software is meant for their hearing aid, and the software is pretty darn complex, but it takes real ear on our part to finish the job, to verify. Verily, verily, is that really the truth? You know, are we getting what the software said we'd get? So that's where this course kind of ends. And there's going to be there's an article by Gus Mueller and a woman by the last name of Sanders, and you could see that at the tail end in those units. I'll just share that with you right there just to show you that unit, okay? Here, Sanders. 2015 article in the Hearing Review. Excellent article. I mean, if I pull this puppy up here, this is a great article, and I'm going to be encouraging everybody to check that out. Manufacturers NAL 2 fittings fail real ear verification. Okay? And it's just unbelievable. One more reason why real ear, in other words, probe mic, that's real ear, verification is crucial in any best practice protocol. So we'll be going over this article in our final unit of the course. And the article is a very, very good article, and I think anybody ought to be reading this article that's not doing real ear. So we will look at that and when we are done. So without any further ado, let's start in our unit number 1 and review what you've had last year in non-electronic acoustic modifications. And I'll bet you dollars to donuts you'll recall this as our very last unit that we had in 110 acoustics. This is how we finished your acoustics course, was in non-electronic acoustic modifications. So, looking at that in a Word document and also in our good old PowerPoints. Non-electronic means there's nothing to do with the guts of the hearing aid inside. It's simply the shape of the hearing aid, the length of the tubing, and the size of the venting. And we just want to make sure that as we exit stage left, as OTC grads coming to be within the next few months, okay, that you basically have our house in order regarding non-electronic acoustic modifications. The biggest one is venting. Okay, the other two, horns and filters, don't really cut it anymore. So we won't spend much time on those at all. But it's basically a lost art. Most hearing aids today are digital, which allow for amazing amounts of frequency shaping. But never forget the resonance of the outer ear canal. I'm hearing something. Ding, 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 ding. I don't know, something's dinging away here. I don't know what it is. Anyway, your outer ear canal is a cylinder open at one end. It's a quarter wave resonator, so it resonates when 1/4 the length of the sound wave. Your ear canal is 2.5 centimeters long, basically 1 inch. So it's going to resonate best with sound waves that are 10 centimeters long. In other words, 1 meter. That's what I'm highlighting in gray. And frequency equals speed of sound over wavelength. Wavelength equals speed of sound over frequency. So if you just plug in the numbers, wavelength equals speed of sound over x. You want to find out the frequency. So 350 or 340 divided by 0.1 is equal to 3,400 hertz. So the resonating frequency would be 3,400 hertz. Frequency is speed of sound divided by wavelength. So you could take this formula here and flip it around. You could just say this. Frequency equals speed of sound over wavelength. And what's the wavelength here? 0.1 meters. Okay? So 1 times 340 is 340. 340 divided by 0.1 is 3,400. But your ear canal is not made out of steel, it's made out of flesh and bone. And so that resonance is spread out. And it's spread out from about these frequencies here, with the peak resonance being about here. Okay? And in your PowerPoint, as you would recall, that is definitely going to look like this. And there's your good old resonance of the outer ear canal. The point is, as soon as you stuff something in an ear, you have lost that resonance. So you've lost that resonance. You're putting something into the ear. Here's your open ear canal. You would have that resonance, which, by the way, sounds to you and me perfectly normal. When you plug up your ear, the frequency response of the hearing aid may look like this, but because you've lost part of that resonance, you're not going to get everything. Okay? So, essentially, that's what this whole first paragraph is talking about. Hearing aids plug up a canal and destroy that natural ear canal resonance. And so the hearing aid has to restore that, bring it, add gain to bring it back, but also make up for the hearing loss. So 2,000 to 4,000 hertz are very important for understanding speech. And some ear molds don't allow enough highs to get into the ear. And how come? Because for some high power hearing aids, BTEs, the tubing may have become narrow. In other words, if I show you this, the tubing in a BTE, let me pull out my little OTC bag of hearing aids again and stop sharing. In a good old BTE, and I'll stop sharing and I'll hold up the hearing aid. If you see somebody with a high power BTE and the tubing is cracked or dry, very dry, when it dries, the plastic becomes brittle. It's no longer soft, and it actually ends up looking pinched. And if that's the case, you are going to lose a lot of high frequencies. Narrow tubing cuts off the highs. It ain't rocket science. I'll take a piece of paper. I'll roll it up like a horn. You've seen me do this crap before, okay? if I talk into the wide end of the horn, you're going to lose a lot of the high frequencies of speech because the highs are trying to get through a narrower hole. If I turn that sound upside down, now you hear the high frequencies really well. Okay? Highs, when you open something up, highs get through. I don't know why, I'm not a physicist. But narrowing of tubing screws up high frequencies. That's a non-electronic acoustic modification. See what I'm talking about? Okay? In the old days, what we did, and people don't do this anymore, but in the old days, we used what was called, let's see if I can find that sucker. I don't think I got it here. This is probably it. Yeah, there you go. Yeah. It was a horn. The tubing actually got wider as it got into the mold. It was narrower at the top and it got wider. It flared out. And they called that a horn. And they actually provided, they called it a 3 millimeter horn because the internal diameter of number 13 tubing is 2 millimeters. It's hard to see. There you go. That internal diameter is 2 millimeters. And a horn, the end, is 3. So you're flaring out. And that was an old way of increasing high frequencies. And that's why I say if you get a client coming to your office who's wearing a high power BTEs and the tubing looks old, it's no longer going to be nice pliable tubing. It's going to actually be pinched. Replace that tubing. Get it out of there and put normal, fresh, new number 13 tubing in, and your client is going to be a lot happier. Okay? So that's a non-electronic acoustic modification. Sharing once again. Okay, what else can I lie to you about? Tell you about here. Okay. Moving on down. All right. You all know this is nothing new for you. Ear mold types and materials. You know that lucite skeleton is the most common type of ear mold used in regular BTEs. So if I pull that out and stop sharing here. Here's a lucite skeleton ear mold. You've seen this 1,000 times. Not that popular anymore because so many people are wearing RICs. Okay, but you still see this. You see this, can you see that second hole in there? That, of course, you know is the vent. One is for the sound, and the other one's the hole in the mold for the vent. And if you turned it all the way around, you'll see the 2 holes at the very end. It's kind of hard to see if I don't know. I'm trying to show you here. There's 2 holes there. One hole is for the sound, and the other one's the vent. Okay? Lucite skeleton, or you might have seen what they call, when they completely plug up the ear with silicone because the guy's really got a whopper of a loss, and now he's wearing, silicone mold that's completely full. Anyway, I'll show you a picture of that as well, just because we have it. And then we'll move on to the venting. You've all done ear mold impressions. You've all done this stuff before. Nothing really new to you there, so I don't need to spend the time. Unless you have questions about it, feel free to ask. You all know that the ear canal has 2 bends. And so you want to really be able to reach that second bend when you're doing a deep ear mold impression for a completely in canal hearing aid. But here's what I meant. On the left, there's your silicone full shell for a whopper of a hearing loss. Here would be that lucite skeleton mold that I just showed you earlier for a hearing loss that's almost a whopper. And also some RIC hearing aids, as you may have seen, have custom ear molds made as well. Have you done that, or have you seen that in clinic at all? Okay, so a lot of times RIC hearing aids, if the guy has an unusual canal or doesn't quite like the dome on the end of the RIC hearing aid, he or she may opt to have a custom ear mold made, and that will be made out of lucite. So it may look a little bit like this. All right. Oh yeah, blah 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 blah. Okay. Ha! Did I ever show you this picture? There was a person at Conestoga College in Kitchener, Ontario, Canada. They have a 2-year HIS program, like yours. And they were doing ear mold impression material practice, and the young woman had a stud in her ear. And I guess the student taking the impression did not make sure that the silicone didn't involve the stud in the student's ear. So the impression material surrounded the metal thing in her ear, and they had to break it all apart in order to take out the ear mold impression. So it's just kind of like, took 15 minutes of very careful cutting to free the impression, because it got stuck on a barbell piercing of one of the Anyway, so you all know why the outer ear canal has the resonance that it does. It's very important to retain this knowledge. Never forget, it's because the high frequency consonants are soft, and you need that natural boost of the outer ear canal as a quarter wave resonator in order to improve the soft high frequencies of speech. And please remember, when you plug up an ear with a hearing aid, you've lost that love and feel, and I'll keep my daytime job, but you know what I mean, okay? You've lost the resonance of the ear. So the hearing aid has to deliver that, has to make up for the fact that because the ear now is closed on both ends, it no longer is a cylinder open at one end. And the cylinder open at one end, like my cup, is a quarter wave resonator. A cylinder closed on both ends is no longer a quarter wave resonator. And that's why this resonance is then gone. The three types of acoustic modifications are often shown to be venting, damping, and horns. We don't use horns anymore because digital hearing aids are very good at amplifying the highs, so we don't have to rely on this acoustic modification. The thing you need to know about it is old tubing in BTEs tends to shrink and narrow. And when you've got it narrowed, you're going to lose some high frequencies. That's the essence in which you need to know about the horn, okay? Damping deals with filters, and filters are barely used in hearing aids anymore either. So we won't go on about that. It's mainly venting. So here's venting on the left. Here's filters, what they used to be, and here's horns. Notice the tubing gets wider. The narrower the tubing, the less the highs. If sound is going this way, you increase the highs. If sound is going this way, you lose the highs. You all know about select events. In case you're looking at a vent that's been put into the mold of a hearing aid, sometimes you can choose the size of the plug. The bigger the hole, the more the vent. And you should know that vents range from 1 millimeter to 4 millimeters. 1 millimeter to 4. If it's a 1 millimeter vent, it's not going to do anything. A 1 millimeter vent is just meant for acoustic comfort. A 1 millimeter vent is great so that when you take the hearing aid out of the ear, you're not sucking out an ossicular chain to go along with it. You're not pulling out the eardrum, okay? It enables a little bit of air to be in the ear canal. If the vent is wider than 1 millimeter, now things happen. What do vents do to sounds? What do? They do, so what would you describe? If somebody was saying, why am I wearing, what's this hole in my hearing aid for? Why do people have vents?
Is it to help with occlusion?
Yes, to help with occlusion, okay? Vents allow the lows to escape. And what is the occlusion effect? Your own voice is louder when your ear is plugged. So right now I'm hearing myself louder in my right ear because I'm plugging my right ear. And what's the real definition of the occlusion effect? Low frequency, bone-conducted sounds resonate the mass of the skull, which in turn resonates the cartilaginous portion of the ear canal. Plugging the ear prevents that from escaping. I always said it. I've said it in 120. I've said it in almost every course I've ever taught. There's 5 things. Low frequency, bone conducted sounds resonate the mass of the skull, which in turn resonates the cartilaginous portion. Plugging the ear prevents that from escaping. That's why you got to use a vent to unplug the ear. And what do vents actually do? Let's read it in our notes. How come they work? Let's go to our notes and escape out of here and read under venting. A short, wide hole in the ear mold done to reduce low frequency amplification. How do they work? It creates more acoustic mass. The air trapped behind the mold is allowed to communicate with the air on the other side. So now you've got a bigger volume of air. And lows resonate with mass. So lows are going to follow mass like Hansel and Gretel followed the breadcrumbs to get out of the woods. Okay? So you've created more acoustic mass, thus allowing the lows to leak out. Larger vents, more lows escape out. Venting reduces occlusion effect. And this is especially, of course, for people who have good low-frequency hearing and who have high-frequency hearing loss. So, noise-induced hearing loss, sloping hearing loss, anyone with better hearing in the lows, poorer hearing in the highs. If you've really got a precipitous dropping hearing loss, 4 millimeter vent. But you have to be careful with venting, because the bigger the vent, the more the feedback. Because what's feedback? High frequencies bounce. Lows bend and highs bounce. Sam's drinking on the job. I'm not sure if that's Pabst Blue Ribbon or what the heck it was. It looked like he's going shh. All right, so high frequencies bounce. So high frequencies are going to bounce off the eardrum, and they're going to leak out the vent, and they're going to get picked up by the mic, amplified, hitting the eardrum, leaking out of the vent. So there's a tug of war between venting and feedback. The venting, the guy has good low hearing but poor high frequency hearing. You want to emphasize those highs, and you want to vent to reduce the occlusion effect. But if you're providing a lot of high frequency gain, it's going to leak out of the vent. So you have a bit of a tension. And your goal is to make sure you meet in the middle. Now, of course, you can use automatic feedback reduction, digital feedback reduction, but digital feedback reduction is kind of scary because it's good to use, but be careful because it really cuts out the highs. Anybody been fitting using digital feedback reduction? Take a Phonak hearing aid, for example, or an Oticon, and use the automatic feedback reduction. And you're going to notice there's going to be a limit on the amount of high frequency gain that you're allowed to provide. It won't let you go because any more is going to create feedback. You're using that automatic feedback reduction. So sometimes when you're using feedback reduction, you tend to throw the baby out with the bathwater. You want the high frequency amplification for the guy with high frequency loss, and you're using the automatic feedback reduction provided by Unitron software or Phonak software, and you implement that, your heart's on your sleeve. You want to do the right thing, but you know what? You're losing high frequency gain. So all of these things come into play. And there's no one right answer. I just want people as budding new clinicians to realize that it's not a straight, simple roadmap all the time. It's, you want to kind of do the best you can. You want to provide the most high frequency gain you can without at the same time sacrificing comfort of the hearing aid. You don't want the hearing aid squealing every time the guy turns around either. So there's a bit of a tension there. This is something to look at. So here we go. Select event is not always that common anymore. For large BTEs it was, and it often looked like this. Show it to you. I'll stop sharing and I'll just show you what select event looked like. little thing with, see how the holes get bigger and bigger? If I put something behind it like a piece of paper, you can see the holes getting bigger and bigger, okay? I don't know. These are select event plugs. The hole was dug in the mold, and then you could choose which one of these you wanted to push in the hole. And that way you could choose the size of the vent that you wanted. And there was no right way. It was just choose one, whichever one works the best. Well, today's hearing aids are mostly, these guys. So when you're using this, look at the vents there. Look at that sucker. It's got 3 big holes in it. Okay? So there's a dome with 3 big holes. This is at least a 4mm vent. So this is going to be great for someone who has excellent low frequency hearing and quite a high frequency hearing loss. So today's hearing aids tend to use vents as well in the dome. And some domes are tulip domes. In other words, they don't have as much holes in them. Some domes are completely closed. So you, the clinician, are choosing the dome you are using in the same way that clinicians yesterday used to choose the select event. Because in the old days, all molds look like this. And today, and you use this to choose what size of vent you wanted in this mold. Today, you're choosing, of course, you're choosing the dome out of the box to choose the vent size for the person. But always remember, the size of the vent is going to interact with the feedback given by the hearing aid. And you got to find the right balance between venting and excess feedback. And it may be a compromise on both ends, especially for the person who's got good hearing in the lows and a hearing loss in the highs. So, all right. In the old days, people used to talk about parallel vents versus diagonal vents. Well, that just meant here's a parallel vent. Here's a diagonal vent. You don't have to worry about that because we're mostly dealing with domes today. But if you are dealing with lucite skeleton ear molds, always try to have a parallel vent. Diagonal vents suck. Okay, diagonal vents tend to let the highs out as well as the lows. Now when you look at, in your notes, you'll see something called pressure vent. And a pressure vent is a 1mm vent. Okay, a pressure vent is only a comfort issue. It's not really going to modify the acoustics very much. It's the smallest vent you can use. The smallest vent you can use. Back to our PowerPoint slide here. This is an important graph. You may have seen this on various midterms or final exams. So here you go. You got frequency on the horizontal. You got dBSPL on the vertical. And look at the venting effects on the low frequencies. A closed ear mold isn't letting out any of the lows. A little bit of a vent, a bigger vent, larger and larger, you're letting out more and more of the lows. Looking here, this is in terms of output, dBSPL, and this one here is just in terms of gain. Same thing. The larger the vent, the more the lows escape. And what is the range of sizes of vents? Generally from 1mm to about 4mm. This isn't even showing you a 4mm vent, but vents, 4mm is about the biggest vent you can have. So now going to our good old Microsoft Word stuff here. Filters are not used that much anymore, so we won't spend a lot of time on filters. Filters were used because of this. They reduced feedback. And if you look at what feedback is from, have a peek at this picture here. This picture is showing you the frequency response of a fictitious hearing aid made in the town of Ordinary in the state called Normal. Okay, and the guy's name is Joe Average. So you're looking at a frequency response of some hearing aid, and you're going to notice bumps. And you'll always notice that in hearing aids. Anytime you measure a hearing aid, you're going to have little bumps. And the bumps are usually in the highs. And the bumps are what cause feedback. The bigger the bumps, the more the feedback. So what you wanted to do was to get rid of the bumps. Get rid of the bumps. If you get rid of the bumps, you get rid of the feedback, no? So what were the filters? They were screens. And if you have a lot of wind blowing through a screen, you're going to hear, okay, screens provide resistance. And resistance is not opposition due to mass, and resistance is not opposition due to stiffness. Resistance in any object is equal for all frequencies. So they would put little screens in the hearing aid, and the screen in the hearing aid would look something like this little red, I don't know if you can see that guy here, there's a little red dot. See that in the hook? Right in there, little red dot. Or the screen might look like, oh shoot, I'll pull up another hearing aid. Might look like this, see that little gray thing at the end? If you looked inside, it would be a tiny little screen. So that screen provided what we called resistance. And resistance is futile. That's what the Borg on Star Trek always used to say. The tighter the screen, the greater the resistance. And the resistance in any object is equal for all frequencies. And so filters dampened the peaks wherever the peaks could have been. So filters, the tighter the screen, the more you got rid of the peaks. Today, we don't need to rely as much on filters. You see, and filters were measured in ohms. The tighter the screen, the more you got rid of the peaks. The more you got rid of the peaks, the smoother the hearing aid sounded and the less feedback you got. But today, we don't need that anymore. That was analog. Today, we have digital feedback reduction. And you know how digital feedback reduction works? We covered that in 240 last year. The hearing aid senses the feedback, and then it measures what frequency the feedback is occurring at, and then the hearing aid produces the same frequency in opposite phase. It's called phase cancellation. But remember, when you're using phase cancellation, you tend to cut out the highs of a hearing aid. So you may be trying to emphasize the high frequencies of a hearing aid, but you are limiting the amount of high frequency gain you can give because you're using that automatic feedback reduction to get rid of the feedback. Feedback is mostly a high frequency phenomenon formed by peaks in the frequency response of a hearing aid. What part of the frequency response? The high frequencies of the frequency response. Okay? So filters were another non-electronic acoustic modification to get rid of feedback. Vents are a non-electronic acoustic modification to deal with the occlusion effect. Horns were a non-electronic acoustic modification to increase the highs. And we talked about horns at the beginning because if you talk into a horn backward with the wide end, you're going to cut out the highs. So you can even imitate, if you want to imitate to someone how elderly people hear, talk backward and talk into a backward horn. That's how elderly hear, because they can't hear the highs. Okay? So what hearing aids, of course, want to do is to take that sound and turn it upside down. But anyway, if you're talking this way into a horn, you're increasing the highs. If you're talking this way, you decrease the highs. And that's why I mentioned to you about old tubing in BTEs. If it gets narrow, you're doing a real disservice. Yank out that dang tubing and replace it. Okay? Great, just great. It's really good to see you all again. I hope you had a great holiday. You had a long holiday at OTC. I mean, classes didn't begin until yesterday. Holy smokes. I think at Douglas College we had started already on the 2nd of January. Like, right away. Good old OTC. Well, we're starting on the 14th. I'm going, yes. Gotta like it. So what else are you guys taking this semester? You're taking 250, and what else?
oral rehabilitation.
Ah, from Rebecca Krause?
Yeah.
Good. Okay, good. That's a good course too. All right, and then do you have a clinical practicum this summer after that or not?
No, this spring is the last one.
Far out. So when you're actually going to be graduating then? In what month? You're going to come
May.
in May?
Mhm.
Cool. All right. Are you all going to, do you all dress up in the graduation garb with the mortarboard hats and the long robes and all of that?
I suspect that will be encouraged. I'll be trying to avoid it.
I'll bet it would be. I'll bet it would be. Hang on a second here. I just happen to have mine from University of Oklahoma. This is all my crap. This is the thing I got to hang around. I just happened to have it here. I didn't know I was going to be talking about this today, but it just happens to be in this little cupboard here. It's from OU, so anytime I attend a graduation, I have to wear that. Kind of weird, huh? OU's colors are crimson and cream. So that's yeah, weird. Anyway, so basically that kind of ends our discussion on non-electronic acoustic modification. So I'll just share screen here and see where we are in our notes, but I think we are about at the end of it. So there's your PowerPoint slide. This is, again, don't worry about this slide, placement of filters. Nobody does that anymore. This is showing you if you're exiting a horn, you're increasing the highs, and if you're entering the horn, of course, you're decreasing the highs. So people used to talk about horns like this. 2 millimeters expanding into 3, 2 millimeters expanding into 2.5, 2 millimeters staying at 2, 2 millimeters shrinking down to 1.5, 2 millimeters shrinking down into 1. So remember how this ties in with how we began this talk. High power BTEs with old tubing act as reverse horns. They literally act like the bottom two. You're decreasing, you're cutting off the highs. So here's the general makeup, as you know, of those old high power BTEs. Again, the high power BTE, the filters were usually here or here. Here you can see a vent. And again, that's just in those kind of hearing aids using number 13. The location of filters was often at the end of the ear hook, as we saw. Good old number 13 tubing. What's the internal diameter of number 13 tubing? 2 millimeters. 2 millimeters. Quiz question. 2 millimeters. Okay. Thin tube, not Rick, but thin tube. Always good to hold a distinction between the two. They look identical. Thin tube, the internal diameter of the tube is only 0.8 or 0.9 millimeters. In other words, less than half the diameter of these. Okay? So they too would cut out the highs because they're thin tube. So the manufacturers of these know that they have to really produce a lot of highs because you're going to lose a lot of them going through that thin tube. Okay? So then remember, where would the receiver be of this hearing aid? It would be up in here. The mic would be here, the receiver would be here, and the sound would be traveling through the thin tube. Of course, as we know, thin tube, open fit. Large vent, okay, open fitting. And look at what the thin tube effect is. It cuts out the highs compared to the regular sized tube. The RIC hearing aids, of course, are even more popular. And of course, the receiver with a RIC hearing aid is here. And there's a big open dome. So the mic of a RIC hearing aid is here, but the receiver is here, as you know. And of course, a wire is connecting the two. So sound isn't going through this at all, of course. Electricity is going through here. The receiver is in the ear. So basically, a good old resound RIC hearing aid. You can see the wire going through. And that's the end of my talk. There you go. We'll go to our notes and see if we finished, but I think we did. So, good old notes. Where are we here? Notes. Notes. Pull up the notes. Okay, horns not used much anymore. Don't worry about these numbers here like this on filters, because that's all yesterday's news. Okay, so don't concentrate so much on filters. Just know what they were used for. And today we've replaced filters with automatic digital feedback reduction. Horns, not used much anymore either in today's digital hearing aids. The thing I mentioned them for is remember the narrowing of old tubing and high power BTEs. Tubing and BTEs, remember number 13 tubing has a 2 millimeter diameter. Open fit tubing, 0.8 to 0.9 millimeters diameter. And essentially today's RIC hearing aids, all of that is academically moot because the receiver is in the canal anyway, and sound ain't going through any tube. So there. So there. Look at these maps. See those old maps? South America. Those are from like the 1950s. Do you know where I got those from? OUHSC. Oklahoma City, the doctoral program, used to be a school for the deaf, for kids. And they had these old maps. They're classics. And I asked the head of our department in Oklahoma City, I said, can I have those? She goes, yeah, sure. We don't want them. Great. Took them. Heavy. You can roll them down. Next week, you'll probably see North America pulled down. And then the next map is United States. And then the next one is Oklahoma. It's great. I love it. Anyway, neat to be way up here. What's it like by you guys in terms of weather? What you guys going through?
We're
Winter's
doing really good.
50 degrees right now.
Oh, that's good. Yeah, so are we. We're about 52. Yeah. We had a lot of rain this winter. I heard, though, didn't the Midwest get a heck of a snowstorm or something like that? We saw it on TV. The whole interstate was plugged up and trucks rolled over. But that was, what, last week, right?
Yeah, and north of us.
Yeah,
North of you.
it's Springfield.
Yeah. So you didn't get touched too much by it in Springfield.
Yeah.
Here we haven't had snow yet all winter. It still rains and rains. I'm looking for Noah's Ark sometimes. It's coming. Oh, well, at least liquid snow, you don't have to shovel it. Okay, you guys, it's great to see you all again. Really glad some people showed up. We'll talk about it, we'll review ANSI testing, just to make sure we've got our act together with ANSI testing, and then we'll launch into fitting methods and launch into real ear and stuff and things and stuff. All right. Good stuff. I'll shut my face now and grab that second cup of coffee, and yeah, maybe I'll have a beer after. Okay. Adios. Live long and prosper.